let's look at chapter 5 regarding our understanding in the axis stress series. And today we're going to be looking at compatibility equations. So what is the concept of compatibility? The concept of compatibility becomes a very useful tool when we're dealing with components of varying cross sections. So in this particular diagram, we've got some form of step down bar of circular cross section. However, we realize that one section is larger than the other. So let's assume that we've got a component where one section has a length that varies from the other. So we're assuming that the length of one section is equal to L1, the length of one section is equal to L2, and both are being subjected to the same measure of force. So we can then use this information to create some form of expression for us to work around this measure of indeterminacy by assuming that F1, or the force in section 1, is equal to the force in section 2, thus equal to F. Thus, if we use the relationship regarding force, stress, and area, we can then assume that the product of the stress and the area in section 1 is equal to the product of the stress and area in section 2. Thus, we can also assume that the final length, L subscript F, is equal to the original length of the component plus the change in length, or the total change in length. The original length of the component, L0, is equal to the sum of the length of section 1 and the length of section 2. Thus, the total change in length, delta L subscript T, is equal to the change in length experienced in section 1 plus the change in length experienced in section 2. So this enables us to establish some form of relationship for us to predict what the variation in stress is in a component similar to that of this stepped bar. So let's look at a simple example to reinforce what we've just discussed. In the diagram, we've got a component that's being subjected to a force of 5 kilonewtons. We've also been given further information regarding the geometric parameters of this given step bar. So section 1, or one of the section has a diameter of 60 millimeters, the other has a diameter of 25 millimeters. One section has a length of 60 millimeters, so that's the length of the section that has a diameter of 60 millimeters, and for the section that has a diameter of 25 millimeters, it has a length or a span of 40 millimeters. We're being tasked to calculate the magnitude of stress and strain in each section of the step bar. And the second challenge is for us to predict or to work out the final standard length of the bar if we assuming that the Young's modulus of the material for this given component is equal to 200 GPa. So how do we go about working through this problem? We know that the tensile force is the same in both sections. Thus, if the force in section 1 is equal to the force in section 2, then we can assume that the product of the stress and the cross-sectional area of section 1 will be equal to the product of the stress and the cross-sectional area of section 2. So, knowing that, we can use the information provided to calculate the cross-sectional area of section 1. So area, since we have a circular section, will be equal to pi d1 squared divided by 4. So we're assuming that the diameter of one section is d1. So we're assuming that the largest section of the step bar is characterized by d1. Thus, pi times 60 squared divided by 4 computes to give a value of 2827.43 millimeters squared. Again, it's more or less up to you if you want to convert your units from millimeters to meters. We've calculated this cross-sectional area for section 1. We're going to do likewise for section 2. So section 2, the area for section 2, we're denoting that as A2, so that will be equal to pi times d subscript 2 squared over 4. So we're assuming that d2 is equal to 25 millimeters. So if we do the needed substitution and we do the computation, we get 490.87 millimeters squared. We can then proceed to calculate the stress in one section. So we're going to calculate the stress in section 1 using the fundamental formula of stress is equal to force over area. So in this case, sigma 1 will be equal to the force divided by the cross section of section 1. So that will be equal to 5,000. So don't forget this is 5 kilonewtons. So 5,000 divided by the calculated cross section of divided by A1, which is 2827.43, and that will yield a stress of 1.77 MPa. So using the relationship that we've already established, if we assume that the tensile force is the same in both sections, sigma 1 times A1 is equal to sigma 2 A2. We can make sigma 2 the subject of this relationship, thus to predict the stress in section 2, sigma 2 is equal to sigma 1 times the ratio of A1 to A2. Thus, sigma 2 is equal to 1.77 times into bracket area 1, which is equal to 2,827.43 divided by 490.87. And that yields a value of 10.19 MPa. Now that we've calculated the stress, we can then proceed to calculate the final extended length of the step bar. So in the previous slides, we deduced that the final length due to the applied load, so that is L subscript F, will be equal to L subscript 0 plus delta L subscript T. Delta L naught characterizes the original length, and delta L subscript T characterizes the total extension. And the total extension change in length experienced by the component will be equal to the change in length in section 1 plus the change in length in section 2. So what we can do is we can proceed to calculating the extension in each section. So we know that strain is equal to delta L over L, and we also know that strain is equal to the stress divided by the Young's modulus. Fortunately for us, for this particular example, the material is homogeneous throughout. So the component is made out of one specific material. Thus, the Young's modulus in both sections are more or less the same. So we can use this information to calculate the strain. So the strain is equal to the stress divided by the Young's modulus. So epsilon 1 is equal to sigma 1 over E, and we do likewise for section 2. Epsilon 2 is equal to sigma 2 over E. So this is more or less a choice. You can either use this concept to predict what the strain is and individually calculate the extension in both sections, add the two to work out what the final length is. Alternatively, we can use this information to establish an equation. So what we've done here is we've substituted what the change in length is with respect to the stress and the Young's modulus, and substituted it into the equation delta LT is equal to delta L1 plus delta L2. So if we do the substitution, we get delta LT equal to, into bracket, sigma L over E for section 1 plus sigma L divided by E for section 2. So what we can do here is we can factorize the common term. So the common term here will be the Young's modulus, which is, as we've more or less stated previously, the material used for this particular component is homogeneous throughout. We factorize the Young's modulus, we get 1 over E into bracket sigma L for section 1 plus the product of sigma L for section 2. And all that we have to do here is substitute into the equation all known variables. So we know E's been given as 200 times 10 to the power of 9. We've calculated the stress for section 1 to be 1.77 megapascal, so that would be 1.77 times 10 to the power of 6 multiplied by its length. So the length was given as 100 millimeters. In this context, we're converting it into meters, so we're going to divide it by 1,000 or multiply it by 10 to the power minus 3, plus into bracket the stress in section 2, which we calculated or deduced as 10.19 megapascal, so that will be 10.19 times 10 to the power 6, multiplied by 40 times 10 to the power minus 3, okay, or 0.04 meters. And if we do the computation, we get a value of 0.0029 millimeters. So that will be the total extension. So all that we have to do is then add it to the total original length. So the final length of extension due to the 5 kilonewton stress will be equal to 140. So that will be the 100 for section 1 plus 40 for section 2 plus the total extended length, which is 0.0029, which gives a final result of 140.003. There we have it. So let's look at other situations. So in this particular example, we've got a situation whereby the same amount of force is being applied to a component that's constituted of 2 materials, similar to a bimetallic strip. So in this particular example, conditions are such that the change in length experienced by both components are more or less the same. So how do we go about deducing an equation of compatibility for us to work through a component with indeterminate parameters? So this is what we do. We can assume that the change in length in material A is equal to the change in length in material B. If this is the case, then this means that the strain in material A will be equal to the strain in material B. If we assuming that the original length will more or less be the same due to the applied force. So since we know from fundamentals, which we've done previously, that the strain is equal to the stress divided by the Young's modulus E, then this means that the ratio of the stress and the Young's modulus for material A will be the same as the ratio of the stress and the Young's modulus for material B. Thus, in calculating the stress in any given material, so in this context we're more or less creating a relationship in calculating the stress in material A, then the stress in material A will be equal to the stress in material B multiplied by the ratio of the Young's modulus for material A with respect to the Young's modulus with respect to material B. So this enables us to establish this relationship here. So since we're assuming that in this context that the force experienced in material A is the same as the force experienced in material 2, then we can then establish another relationship in regard to the area, whereby the areas are more or less not the same. So we have a situation whereby we have different materials and different diametric profiles, then this would deduce this formula where the ratio of the cross-sectional areas for material A with respect to material B will be equal to the Young's modulus or the elastic modulus for material B with respect to material A. And there we have it. So let's look at another situation. And this time, we have a situation whereby the forces experienced in each material may not be the same. So, what are the things that we do know based on the information provided? The information provided states that the two materials are different. So material A is different from material B. We know that the original length will more or less be the same. And we've been given information regarding the change in length. And the measured extension will still be the same for the given material. Thus, if we assume that the change in length for material A will be the same as the change in length for material B, thus the strain experienced or measured in material A will be the same as the strain experienced in material B. Hence, since we know that the strain is equal to the ratio of the stress to the elastic modulus, then the ratio of the stress and the Young's modulus with respect to material A will be equal to the ratio of the stress to the Young's modulus for material B. Thus, we get more or less the same relationship that we got previously, that sigma A, or the stress in material A, will be equal to the stress in material B times the ratio of the Young's modulus for material A with respect to material B. However, if we assume that the forces experienced, the internal forces experienced by each component are not the same or not equal, and that the sum of the forces within the material is equal to the deformant, the external force, then if we're also assuming this relationship, then we can then proceed to deduce another relationship with respect to the force. So, since we know that sigma is equal to F over A, we can use the F over A formula to redefine the formula with respect to stress. Thus, F divided by A with respect to material A will be equal to the ratio of the force and its area times the ratio of the elastic modulus of material A with respect to material B. So if you wanted to predict the force in any of these materials, so in this particular example, we're looking at the measure of the force regarding material A, then the force in material A, so F subscript A, will be equal to the force in material B times into bracket the product of the sectional area and the Young's modulus for section of material A divided by the product of the area and the Young's modulus for section B. So this enables us to establish another equation for a problem similar to what we have in the given diagram. Let's look at the last and final example relating to the concept of compatibility. In this particular diagram, we've got the same measure of force causing deformation in two components of different material. Thus, the elastic modulus in material A would be different to the elastic modulus for material B. So if we're assuming a situation whereby the measured extension, the measured change in length in material A will not be equal to that of material B, however, we're assuming that the applied force on both materials are the same and the cross-sectional areas are more or less the same. If this is the situation, then we can assume that the measured stress in material A is equal to the measured stress in material B. And since strain is equal to the ratio of the stress to the Young's modulus, if we then make stress the subject of the relationship, then we'll have the stress is equal to the product of the strain and the Young's modulus of material A will be equal to the product of the strain and the Young's modulus of material B. We also know that strain is equal to the ratio of the change in length to the original area. So we can then modify this relationship as follows. Delta LA over LA times EA, so that's basically the change in length in section A divided by its length original length multiplied by its Young's modulus is equal to the change in length with respect to material B divided by its original length times its Young's modulus. And since the length in component A is the same as the length in component B, we can cancel out the original length to have the following relationship, that the ratio of the change in length of material A to that of material B is equal to the Young's modulus, or the elastic modulus of material B with respect to the Young's modulus regarding material A. And there we have it. Alright folks, so hopefully everything made sense to you. So any comments that you have, can you just type it down below? And hopefully you join me in the next session. So please share and subscribe, and I'll catch you in the next section. Bye for now.